Uh, am I audible? Okay, welcome back to the 11th live session of Solar Energy Engineering and Technology. Myself, Soumya Tiwari. I am PMR Scholar at Department of Sustainable Energy Engineering at Kanpur. So, in today's live session, we will discuss about the week 11 content, uh, which was mainly about thermal energy storage. So, in thermal energy storage, we'll mainly talk about the sensible heat storage, then latent heat storage, the thermochemical storage, and one of another form of heat storing medium, that is a solar pond. So, as usual, for the first um, few minutes, or say 45 minutes, I will just give you a recap of whatever the week's content is, and then at last we'll solve some numerical problem. So, okay. So, what is need of this energy storage? Uh, so, if you know that it's all a play of demand and okay. So we were discussing about what why we need a energy storage. So it's all a play of demand and supply. So basically, we want to meet our demand with our supplied energy, right? This may be in form of electricity produced from your conventional power plants, fossil fuel based power plant, or if you want to couple it with the renewable energy sources. But the problem with renewable energy sources is that it's not consistent, right? It's not consistent throughout the day, throughout the season, throughout the year. If you talk about the solar energy that we have discussed in detail in this particular whole course, then there is intermittency involved with the solar energy. So in the peak hour during the day, the sunlight that we receive is very high as compared to we don't receive any sunlight in the night. So there is intermittency, there is unreliability, right? Someday it could be a cloudy day, someday it could be a clear sky day. So if you want to club renewable energy resources for meeting our demand, then there lies basically reliability issue and intermittency issue. On supply side also, we have not a consistent in demand side also, we don't have a consistent demand, basically requirement, because in the day we use more of our electrical equipments, then our demand is very high as compared to say in night time for a factory, right? So this demand and supply continuously changes. To meet the bridge between basically supply and demand, energy storage systems comes into pictures. So what does energy system storage do? uh, Basically it stores the surplus amount of energy generated during the day, or when say during a summer season, and then store it to supply it when the your energy generation is there, say at the night time or in the winter season, right? So this energy storage basically equipments provide a very steady output, reliable output to meet our demand. So that is whole idea about the energy storage system. Now, you can clearly see this is diurnal variation. Diurnal means for a day. Okay. So how for a typical sunny days, the renewable energy, the power generated by renewable energy changes, right? And this is also for a typical sunny day. Okay. So like you can see this curves. So you can see clearly this one curve is a solar power curve. So between 8 and 16. So from morning 8 to evening 4 o'clock, we have highest power supply, right? In terms of we have maximum sunshine, right? But if we would talk about the wind power, then it's consistent, like till 10, and in day we have a high wind speed, so your generation is quite high, and then it decreases as we move towards evening, and then it's constant. If we talk about the hydroelectric power, we are getting consistent, basically power supply. So this is all the different nature of the curve explaining how this power generated from different renewable sources varies throughout the day. If we compare it with demand, so our demand curve is quite consistent throughout the day, mainly higher in the daytime as compared to the night time, or in a very early morning, right? And this is our production curve. This is also very high during the day. So the purpose of this curve is to understand how the demand and supply varies throughout the day, and then also for a year also. That is another thing. But yeah, so for that we need an energy storage system. It could be a thermal energy, it could be in the form of electrochemical energy, it could be a pump hydro, that is a very common thing. Compressed air energy storage, energy storage by flywheel, it's a mechanical form of energy storage medium. Magnetic energy storage, chemical energy storage, or hydrogen storage. So depending on what temperature range is your application, how much energy density you want, how much cost you want to go for, how efficient your system is there, we decide which basically energy storage system we are going for. So here we'll mainly talk about this thermal energy storage and thermochemical energy storage. Okay. So have I already explained what is the need, how does it work? So basically, when a surplus amount is there, storage is there, and when there is deficiency, then your supply is there from those storage medium. Okay, what is the size of this thermal energy storage medium? That depend totally upon what purpose you are going for. Okay, so depending on whether your demand and supply is consistently happening, and you have to store it for a very small interval of time, then you need a very small storage, very small in size, that is a buffer storage. For a day you have a diurnal system. Okay, and for annual storage, you need a very large long term storage system for this basically type of energy storage system. So you can see this is for a month also, how during a month your load and demand curve basically varies. So uh, during first say few month of the Jan, when sunshine now is not very prominent, your energy collection is very low, and at the as compared to the last say 15 days of few days for of the Jan month, but the demand is constantly constant throughout this basically your load requirement is constant throughout this month. So you need to understand what the curve signifies in term of energy collection or energy production and load requirement. Okay, so we are talking about sensible, latent, and thermochemical. Sensible means uh, basically whatever amount of energy is released by for a particular change of temperature, right? So this equation is well known, equal to mcp delta t, where dt is the change in temperature from T1 to T2, right? If you want to talk about latent heat storage, then it's where phase change is involved. So during phase change, your heat is released or heat is absorbed. So basically, thermal energy from sun could be used to basically change the phase of particular from solid to say liquid, and while it's cool off during night time, then that released energy could be used for meeting our load demand, right? So this is the formula we have already studied, with mass into latent heat of fusion. If isothermal operation is there, where there is involvement of both temperature change and phase change, then this formula comes into picture. So mcp delta t plus latent heat of fusion plus say from T plus to T2 temperature. For this is for solid and this is for liquid, right? If there is a phase change also involved. Now thermochemical chemical storage. So this is another interesting storage thing, where basically solar energy is used to drive some endothermic reaction. So endothermic reaction means there is requirement of some energy to drive that particular reaction. So that we get from thermal energy, and we basically get some product. Now that product is stored, and when where energy requirement is there, a reversible process, a reverse process happen, where that product is converted back into reactant, and in that process, that is an exothermic process, and heat is released. So that is whole idea about the thermochemical storage. Basically this. Okay. So this slides basically summarize all the different material used for sensible latent heat storage. Latent heat storage including organic, inorganic, and other compound. The majorly used are this paraffin, and inorganic this salts and salt electrolytes. So, and in sensible energy storage, most of the time water is used. You might have seen in the flat plate collector also, right? Thermal oil and molten salt are obviously also used. So the consideration while designing a solar thermal, or say just thermal energy storage system, is whatever temperature you are going for. Like what is the operating temperature? So in that operating temperature range only, your if you are going for latent heat, or then that your in that temperature range only your that phase change should occur. Okay. Now depending on what capacity you are going for, depend on what temperature again you are going to design your system. There should be a minimum heat loss, and also the cost should be minimal, right? So those are important for consideration, and that too depend on system to system, whether you're going for sensible, latent, or a particular thermochemical system. Okay, so for solar thermal energy storage system, uh, if you're talking about solar thermal energy storage system, then we also have to see obviously about the availability of solar radiation, and then we have all these three properties, basically three important point, that what the thermal process nature is, what is economic assessment if you are going for solar, or if you are going for some other energy storage system, and then also about what is the physical and chemical properties of storage medium. Okay. So I'll not dig deep into this theoretical part. This was just to give you an introduction. What we'll see is, okay. So let's skip to the numerical part. Okay. So this is the question based on, okay, sensible heat storage. We have been asked to calculate the energy required to heat a 270 liter of water from 15 degrees Celsius to 55 degrees Celsius. Assume that no heat loss is taking place from the tank where water is kept. So we have a tank with some water, right? And then its mass is given, and is basically its mass is given, and delta T is given, right? What is the temperature change where that we need to be done? So it's a basic sensible heat storage problem, where we already know the density of water, the CP value of the water, um, and the delta T temperature change is basically 55 minus 15, that will be 40 degrees Celsius. So we can easily calculate the energy required, that will be mcp delta T, right? So it will be m into specific heat capacity, and delta T is change in temperature. Okay, that will be value of Q. So note that m 270 liter is, m is given in liters, you need to convert into kg, right? So it will be basically mass into your density, and this is your cp value, and this is your delta T. You can calculate the heat, or sorry, energy required to change this temperature for a particular water filled tank. Okay. Now, if you are using a thermal energy, basically uh, storage, then what will be the your saving for electricity, right? What will be your saving, electricity saving, right? So if price of electricity is 6 kilowatt per hour, rupees 6, then you can multiply it with, and you can say that your 74.7 rupees has been saved by using this particular energy storage system. Now, this is an important topic. You need to have understanding of how this particular system has been analyzed. So basically, this is a liquid storage tank in a well mixed situation, and it's basically sensible heat liquid storage tank. Uh, whatever heated fluid is coming from your, say, liquid flat bed collector is fed with into this energy storage, sensible energy storage system. So this is energy storage system. Okay. And this basically energy storage, from this energy storage system your load requirement is being fulfilled. So this is where your q load has been is being fulfilled. So for that, this derivation has been done. You can go back and look into lecture. So the important formula that you need to remember is this formula. This is the final, after the analysis, that the important formula that we get is this formula. Okay, so this you need to remember. And obviously, q useful is equal to mcp delta t. Well, delta is for fluid from inlet to outlet. Okay, so if you remember, this is delta t of fluid inlet and outlet. And for load requirement, we know that whatever mass flow rate is going towards the load, uh, and then the initial and final temperature of those liquid. So we'll see one numerical, it will clear it out in much detail. Okay, so this is a problem of liquid storage tank. So a well mixed water storage unit contains 3100 kg of water. Okay, and is provided with auxiliary heating of 3 kilowatt. So an auxiliary heater is there, 3 kilowatt. Shows the configuration of the system. Data for the useful heat gain from the collector. So useful heat gain from the collector, ambient temperature, and rate of withdrawal to the load. So basically this is m dot load. So whatever rate, at which rate your fluid withdrawal is there towards the load on a particular day from 3 to 12 hour are as follows. So for every hour from 3 to 12 o'clock, this three values has been mentioned in the table. Assume that the auxiliary heater switches on when the temperature in the tank falls below 45 degrees Celsius. So whenever the temperature in this tank, okay, the temperature between this in the this tank falls below 45 degrees Celsius, okay, this auxiliary heater starts to work, and the makeup water enters in it at 24 degrees Celsius, and at the same rate as the rate of withdrawal. So this is coming at 24 degrees Celsius, and m dot load flow rate, whatever flow rate is there. Okay. Now UAT is given. Calculate the hourly variation of TL from hourly variation of liquid in this tank from 3 to 7 hours, starting with the value of 50 degrees Celsius. So at 3 o'clock the temperature is 50 degrees Celsius. Okay. And also calculate what is the time when this auxiliary heater needs to be switched on. Okay, we already know this some specific heat of the water that we will assume it will remain constant, and we also neglect the heat capacity of this particular tank material. Now, considering this assumption, we'll now start seeing how this problem will be approached. Okay, so if you want to calculate the heat capacity of liquid, it's basically MCP, right? So mass of the liquid in the tank into its specific heat capacity, right? So we already know the mass 3100 kg and specific heat capacity is 4.18. This is the heat capacity of the liquid in the tank. This value will be used and again, so that's why it has been uh, calculated separately. Now what's given in the question is that liquid temperature at 3 am is 50 degrees Celsius. If you okay, if you want to calculate what is the load heat, right? So we already know the formula for sensible heating. It will be basically mass flow rate that is going towards the load into specific heat capacity into change of temperature. We already know the ambient temperature also, right? So uh, note that the ambient temperature is not constant, it's also varies throughout the day, with every hour, right? So at ta at 3 a.m., from 3 to 4 a.m. was 16 degrees Celsius, so that's why we have taken here 16. Now the starting temperature at 3 a.m. for liquid in the tank was 50 degrees Celsius. If we'll calculate this, we can know the what is the load requirement from 3 to 4 hours. We can calculate in kilojoule per hour. Now this is the formula that you need to remember. So direct question will be framed on this formula only. Okay. So we know Q load. Uh, Now for the very early in the morning, your useful heat gain is zero, right? So we are not uh, basically getting any heat basically from your storage tank. So your QU will be zero. Okay. U80 is already given in the question. We already know T ambient. We already know the initial temperature for the liquid in the tank, and we know this value. We know rho CPV that we have already calculated here. This was heat capacity of the liquid, and we know the time. So what we can calculate is after 1 hour. This is T is your time. Okay, time in hours. So we can calculate, we know the initial temperature of the liquid in the tank. We know we want to calculate after 1 hour what will be its final temperature. So we'll put all the values in this equation, and this is your unknown term. Okay, this is after 1 hour what will be the temperature of liquid in the tank. We can put all the values and we can calculate what will be temperature of the liquid in the tank at 4 a.m. So from 50 degrees Celsius, the temperature has decreased to 47.65 degrees Celsius. Now, similarly, we know at 4 a.m. Now we can calculate it for 4 to 5, and then 5 to 6, and then 6 to 7, right? Similarly, you can calculate for each of these particular hour gap, right? So if we calculate, then this will be temperature of liquid from 3 a.m. to 7 a.m. So from 50 degrees Celsius, you can see the temperature has gone decreasing to 47 to 45, 43, and then 42. Around 7 o'clock, the temperature changes not as fast as the initial time. Now, if you want to calculate Q load at between 5 to 6, okay, we already know this value, we can calculate directly, right? We can put back into the, so the note that the second question was, at what time does the auxiliary heater needed to be switched on? So it needed to be switched on when your uh, liquid temperature in the tank falls below 45 degrees, right? It was 45 only, right? 45, right? It was for 45 degrees Celsius. If the liquid temperature in the tank falls below 45 degrees Celsius, we can see that uh, okay, so at 4 a.m. it was 47.65, and at 5 a.m. it was 44.46 degrees Celsius, the temperature of liquid in the tank. So the time at which the auxiliary that heater need to be switched on lies between this only, right? So uh, we know that at basically 5 o'clock the temperature was 45.86 45.46, right? And what is the time required for the temperature to be reached to from 45.46 to 45? Okay, so it will be basically in 5 to 6. So you can see the temperature is decreasing with time, right? So from 45.46 to 43.46, somewhere here your 45 degrees Celsius will be reached. So we are basically trying to calculate that temperature at which this particular temperature is reached. Okay, so basically we know TL is now 45. TL initial is 45.46, which was at 5 o'clock, and we know all the other value. We can calculate the unknown T here. If we'll calculate it, the T will come in hour. Note that T always here will be put into hour only. It's not in minute, right? So we can calculate back in minute. So it will be multiplied by basically 60, right? So it will be 13.30 minutes. So from 5 o'clock, we'll add 13.30 minutes, and that will be basically the time at which your auxiliary heater needs to be switched on. So that is the numerical based on your liquid in the tank as a sensible heat storage medium. Okay, hope this question is clear how to approach this type of question. So the main you need to remember this formula. Okay, this formula is very very important. It tells about how the temperature of the liquid varies with respect to the time, with your particular required load, and your continuous your heat useful heat gain. Okay, now stratification is another very important term. Stratification means there is a temperature gradient within the storage tank. Now in a previous question what we were considering, that the temperature of liquid uh, in a this storage tank was constant throughout the storage tank. It was not varying, right? But in actual system, there is some stratification in the storage tank. So as the water get heated, the hot water zone is in above zone of this storage tank, and the low temperature water is in the heavier water is in basically your lower half, or you can say the downside of your storage tank. So that is known as stratification. So this water tank may operate with significant degree of stratification due to density difference. Now this allows hot water to be delivered to the load and cold water to return to the collector. Okay, now you can see how with temperature the density and your specific heat varies. That is another thing. But the concept of thermal stratification is there is a density difference and temperature difference causing the density difference. So hotter zone is in the top of the tank, and the basically colder zone as compared to the above of the basically tank, the colder zone is in the bottom part of your storage tank. So how does it help? It basically reduces the heat loss from the tank, and now your collector, the heat going to the your water going to the collector is now at lower temperature. So the your collector operate at lower temperature also, and your collector efficiency will increase. Now very important heat storage medium is your phase change material. As the name suggests, there is a phase change involved in this particular thermal storage medium. It could be solid to liquid when heat is absorbed, and liquid to solid when heat is released. So this is curve. This was curve for the sensible heat. So this is your sensible heat curve, and this is your latent heat curve. So this is where your at constant temperature your phase change occur, and then it could involve this sensible heat where your temperature again rises. Okay, so this is your latent heat part. So as compared to sensible, your latent heat fusion value have a very high value. Okay, so in a very small volume change, you can get your very high energy density, right? Very high energy in case of your phase change material. Now, the properties that we want in a phase change material is that it should be very stable, it should not degrade with repeated cycle, because it involves many cycle of solidification and liquefaction. And it should have high thermal conductivity. It should not like at low temperature only vapors may be formed, so low vapor pressure will be there. Even if form, its pressure should be low, and it should be non-corrosive in nature. So these are all the benefit and drawbacks. I will not go into detail. These are different type of PCM material with melting point and heat of fusion. So this is typical PCM material where you store PCM material in this seal tube. Okay, and basically as the phase change occur, this heat is basically, if it's going from liquid to solid, your heat will be released and then gas will be heated due to heat transfer between this um, basically seal tube when you're passing gas through this particular chamber. These are different PCM um, options with melting point, heat of fusion, thermal conductivity, and density. Basically, these four are the important parameters that we consider while choosing a phase change material. So that's why it's listed here, depending on whether it's inorganic, organic, paraffin or non-paraffin wax, or it's aromatic. Okay, so these all are listed here. So let's not go into detail. So encapsulation is basically just what I have explained. So PCM material is stored in some basically encapsulation. So this helps uh, to improve the heat transfer, also prevent reactivity towards its environment, and it basically in a controlled volume, your whole phase change is occurring within this controlled encapsulated tube. Okay. The other method to enhance the thermal conductivity could be use of fin or filling, or maybe a uh, graphite matrix, or it could be any porous medium. Okay, so let's not go into detail. Okay, so the thermochemical storage, I've already explained. To drive a endothermic reaction, energy is required, that is we get from thermal energy, and we store that product. And when your energy requirement, load requirement will there, the reverse reaction occur, and then in that reaction your heat will be released. So this is typical example. This is called steam methane reformation, where steam react with methane to get your syngas. This is carbon monoxide plus hydrogen, and this is a very famous reaction, very useful, basically hydrogen production reaction. So most of the hydrogen produced in world today is basically with this methane reforming, especially this steam methane reforming reaction. So we can see the temperature of the forward reaction and temperature of the reverse reaction. So this is, at this reaction, your basically this forward reaction take place, and when your energy will be required, this syngas could basically react back to give this methane and H2O. So this is the energy stored per unit volume of the storage. These are some other reactions. Okay. I think this was enough for an introduction. The interesting part is this solar pond. Okay, so I'll just give you an idea about the solar pond. So it's a very economical way, very easy way how to collect and store a solar energy if you want to operate within a temperature of say below 100 degrees Celsius. So from 60 to 100 degrees Celsius, it's a very good system to store uh, uh, basically thermal energy. So, what is a solar pond? So it's a saline water pond. So basically containing salt, and the concentration of just a minute. The concentration of the salt in this water varies throughout the depth. Okay, so there is a concentration gradient between the top of the this pond and between the this bottom of the pond, and due to this naturally formed vertical salinity gradient, um, basically low saline water, fresh water will float on the top, and high saline water due to high density will be settling down at the bottom. And as the layer of salt solution increases, the concentration with depth also increases. And at the base where uh, at a very depth, this has a very high uniform salt concentration. So this is the history of the solar pond. First, it was invented in Israel for maximum temperature of 100 degrees Celsius, and in India also we have such pond in Gujarat. So okay, this is the important thing. So as the depth increases, this concentration gradient increases. So this is at top and this is at bottom. So density and concentration at the top is different than the density and concentration at the bottom, and the temperature also varies, right? So um, what you need to remember is basically density is function of concentration and temperature. From that we get a stability criteria. So this is the stability criteria that you need to remember. So this is how concentration varies with the depth. It depend on basically your density varying with temperature at a constant concentration, and your temperature varying with depth, and your density varying with concentration at constant temperature. So this criteria you need to remember. This is the stability criteria of a um, solar pond with a concentration gradient. So this is the minimum concentration gradient required for maintaining a given concentration gradient at a particular level in a solar pond. So if we'll say, if in question it starts say that at this depth, what should be the concentration minimum concentration gradient to maintain this level of concentration. So you automatically falls back to this stability criteria, and we'll apply this, and we'll see some numerical based on this stability criteria also very soon. Okay, this is the question. So say sodium chloride is used as a salt in a solar pond. Estimate the minimum concentration, a kg of salt per kg of water, required at the bottom of the pond if the concentration at the top is 0.02 and the temperature difference of 65 degree is to be maintained. Okay, so that is the temperature difference that we want out of this solar pond. Assume that the concentration and temperature profiles are straight line, and take the average of value of this change in density with temperature and change in density at with concentration to be this particular values respectively. Okay, so we know that this is your solar pond. Okay, say this is your top and this is your bottom, right? Sodium chloride is used. Okay, uh, what's given is okay, if the concentration at the top is, so the concentration at the top is given, say 102. Okay, this is per kg point 0 and 2. Okay, and the temperature difference, so from top to bottom, the temperature difference is delta T is 65 degrees Celsius. Okay, this is 65. Now what has been given is del rho by del T and del rho by del C. We already know this stability criteria, right? That should be there. This stability criteria should be fulfilled to maintain at any depth the concentration gradient. Okay, so we already know this value, right? We already know this value. We already know. So what we don't know is okay. We need to calculate this DC concentration gradient concentration at bottom. Okay, this is C2. This we need to calculate. Okay, So if we put the value, we this is the thing that we get. So the concentration gradient equal to your change in density with respect to temperature at constant concentration upon change in density with concentration at constant temperature into your dt by dx. So this dx will be cancelled, and it will be basically directly proportional to change in temperature, right? So if you know already know dt value, that is 65 degrees Celsius, we'll put it back into the equation. C1 we already know, C1 is 0.02, right? This is 0.02. So we can calculate the concentration at the bottom of the tank, which will be in kg of salt per kg of water, right? This is a very simple question based on how to calculate concentration at any depth of the water to maintain a particular concentration gradient within that particular solar pond. Okay, so this is a very simple question based on that. Now, I'll just summarize how this solar pond works. So we have three zones in a solar pond. This is surface convective zone. It is also known as upper convection zone, or we can also call it a freshwater zone. Okay, this is your concentration gradient zone, where the concentration gradients actually exist. Okay, this is also known as non-convective zone. Here, convection does not occur, so that's why it's non-convective zone. This is surface convective zone. So it's where the surface convection occurs. So the convection type of heat transfer actually occurs at the bottom and bottom and the top layer. And that the last basically zone is this lower convection zone or bottom convection zone, where basically your convection is there, right? So this is very tend to, if the solar pond is around say 0.6 meter, this is a very uh, small zone, 10 to 20 centimeter, but most of the heat are absorbed in this zone. Only 30% of the heat are absorbed in this surface convection zone. If we talk about the concentration and temperature, that is of the main importance here. So if we'll talk about the this is the incoming solar radiation. Okay, so it's most of the heat is absorbed 30% in this zone, and the 30% is actually utilized, and the rest of it is particularly been lost, and then uh, lost to the surrounding and lost to the bottom, and other losses. Okay, so if you see the in upper convection zone, the concentration and temperature is constant. The variation in concentration and temperature actually occur in this non-convective zone. Okay, so this concentration gradient zone. And then at the depth also, the concentration is very high at the like saturation concentration, and this concentration is constant at the bottom layer. Okay, so this is the layer with actual basically high temperature zone, from where your useful heat is basically extracted. Okay, you can see it's clearly mentioned, like if you are getting 100% of incident radiation, the most is lost to the surrounding, and 30% of, okay, we'll see the figures later, but the lower concentration, this is low temperature and concentration zone, this is gradient temperature and concentration zone, and this is high temperature and concentration zone. The useful heat gain is about 14%, and heat loss to the ground is about 2%. Okay, so this solar pond is basically 2 to 3 meter deep, and a very okay, so there is some liner also provided here to basically reduce the heat loss to the ground, and the concentration varies from 20 to 30% at the bottom to top. Okay, now the solar pond has been explained in very detail about how to do its energy balance, how to calculate how much has been transmitted in the pond, how much has been lost to the surrounding, how much has been actually reached to the bottom of the pond, and what is the useful heat gain. And this solar pond has been explained in very detail. So I will not go in detail for this particular topic. You can already go back to the lecture and watch this. What I will do is I will highlight the important formula again. Okay, so we already know the Snell's law. Okay, so this is say your air and this is your water at the top surface. Okay, this is your air and this is your water. That is where your Snail's law comes into pictures. We have already studied this later. So on theta 1 upon sine theta is equal to n2 upon n1, which is ratio of the refractive index of this medium 1 and medium 2. Okay, we have already seen how to calculate this two basically component of the reflectivity rho 1 and rho 2, and the actual reflectivity is your average of these two value, and then you can calculate the transmittivity, or you can directly calculate transmittivity by doing 1 minus this rho value. Okay, so this is a table for particular theta 1 angle and corresponding theta 2 angle for a air and water medium, and some calculated tabulated value for rho 1 rho 2, and your average value and your tau r value. So if the angle of incident of solar radiation into the solar pond is between 0 to 60 degrees Celsius, then most of it is uh, basically to the basically inside the pond. So the loss due to reflection is only about 2 to 6%. If this angle is greater, then the most of is lost to the surrounding. So most of is been reflected back to the surrounding. Now, we have also studied about transmittivity based on absorption, how this Vogel's law comes into the picture. We have already seen this formula many times. And we also know how the intensity varies with depth, right? This formula we have seen. So, a very famous this reversal formula is there to calculate this transmittivity based on absorption, where this A is a constant value depending on A and K are constant value depending on which wavelength we are talking about, which wavelength range we are talking about, and so this is important formula that you need to remember. Now, this is another correlation given by Brandt and Kolbeck. This also X is the depth of the water, and this tau is basically transmittivity based on absorption. But Rebel and Nelson is the widely used formula for calculating transmittivity based on absorption. Now, this numerical explain well about the this whatever we have studied. So, a 2-meter deep solar pond is built in Guwahati. Okay, the value of global and diffuse radiation measured on a horizontal surface on a 15th May at 13 hour are 900 and 200 watt per meter square. Calculate the flux reflected from the water surface, flux entering the water, solar flux at the depth of this 4 depth. Okay, 0.01 to 0.5 to 1 and 2 meter. So we already know the basic drill. So we know the date, we can calculate the n, we can calculate the declination angle, right? 23.45 sine 360 by 365 and 284 plus n. We know the phi value, we know the delta value, we know the omega value also. So it's given 13 hours. So for 13 hours, omega will be, it will be 15 degree, right? It will be 15 degree, and it's basically afternoon, so the sign will be negative. So we know the omega, we know delta, we know phi. We can calculate the incident angle or cos theta 1 angle, right? We know the formula sin theta, incident angle is basically sin phi sin delta plus cos phi cos delta into cos omega. This is for horizontal surface, okay? We can calculate theta. If we know theta, we can calculate the theta 2 value by the Snell's law we have just studied. Okay, this is your Snell's law, okay? We know the refractive index for water and air. This is basically 1.33, and we can calculate the theta 2 value. Now, we know theta 1 and theta 2. Theta 1 is basically 15, and your theta 2 value is basically 11.75. So this is similar to this part, right? So at that value, your rho b is 0.02. From the table, we can directly get this. So the rho b value will be around this only, right? And okay, and the maximum in of theta 1 that we want to see is this 60 degrees. So as I have told, from 0 to 60 degree, most of it make to the pond. So for 60-degree angle of incident, the angle of refraction will be this much, and your rho value will be this much, and tau r value will be this much. Okay, this we can actually get from the table. Now the flux reflected from the water surface. So if this is your solar pond, okay, this is the radiation coming. This is beam radiation, and some diffused radiation will be also coming here, right? So we have already given the global value, which was 900, and the diffused value, which was basically your 200. So we can calculate the beam part or direct part, which will be 900 minus 200, which will be your 700, right? And you already calculated the reflectivity for beam radiation and reflectivity for diffused radiation. So after 60-degree, your basically your diffused radiation comes into picture. So that's why this value has been taken. Okay, so this 0.059. So we can actually calculate how much of incoming beam radiation and diffused radiation has been re reflected from the top of the water surface. So 25.8 watt per meter square has been already reflected from top of the surface. Now the rest of will be entering the water. So the flux entering in the water will be your total 900 minus this 25.8 watt per meter square. This much is actually entering into the water, right? If you want to calculate the flux reaching at the different depth, then we need to calculate the transmittivity based on absorption, right? So we already know this formula for x depth and theta 2 refraction angle. This tau is the value transmitted based on observability. This is the formula we basically use to calculate this value. So we know the x value, x is the depth. So the four values that has been mentioned in the question, we can calculate the x based on your theta 2. This was for beam and this was for your diffused, right? So we can calculate this tau a value. Knowing this tau a value, we can calculate solar flux at various depths. We already know that this is your beam part and this is your diffuse part. Okay. So we can calculate individually the beam radiation that has been reached to the basically at a particular depth, and this is the diffuse radiation that has been reached to your particular depth. We already know the value. We can calculate the solar flux at different value. See that how this with increasing depth, how this solar flux value decreases. So if you'll see that out of 900 watt per meter square, only 87.42 basically goes below the water surface, actually reaches from in your pond. Okay, and this value with depth, how it decreases. So we can see with depth how it decreases from 874.2 watt to your 200 something value. Okay, so the surface convection zone, which is around 10 centimeter, where the most of the radiation is dropped, is between 1 to 2 micrometer wavelength, and about 30% of the incident energy is absorbed in this particular surface convection zone. Okay, this energy is almost entirely lost to the surrounding because of low collection efficiency, obviously, and the flux penetrating to the bottom. Okay, to the bottom is actually this 261 watt. Okay, which is about 31% of the incident energy. So you can see how only a small part of whatever incident flux is there on the solar pond actually reaches to the bottom of the surface. That's why the collection efficiency of such systems, the energy storage systems, are very low, even lower than your flat plate collectors. Okay, so this is temperature, how to calculate temperature distribution and collection efficiency. I'll not go into detail. It's all basically energy balance only. So let's skip this. So these are some obviously practical shortcoming of solar pond, where biological growth, dirt, leaf, and effect of rain and wind induced waves are some shortcoming to this solar pond, including its low basically efficiency, right? So solar gel is another alternative where we include a layer of basically polymer gel tapped in a Tedlar plastic bag in between uh, your surface convection zone and your bottom lower convection zone, and basically it reduces the evaporation loss from the surface, and the efficiency somewhat increases as compared to your natural convection, your solar pond. Okay. So let's directly go back to this numerical. So this is a very important relation, an analytical solution for the annual temperature variation, how the temperature within the solar pond varies annually. Okay, this is given by Rebel and Nelson. If you remember this particular formula, this was for the transmittivity, right? So what does this formula signifies? How to calculate what is the say uh, let's see the term first. Okay, so these third zone is for the lower zone. Okay, so this is annual average temperature in the lower convective zone. This is the annual average ambient temperature. This is your transmittivity, right? This is your annual average global radiation thermal conductivity, and this term you already know, where your L2 is the depth of the water, and Q load is your annual average heat extraction rate and area of the pond. So we can calculate for particular application for a given particular load requirement at a particular location with particular insulation, what will be the area of the pond. Okay, so that is the basic idea about this formula. So let's see with an example. A solar pond located at a place is to be used for supplying heat energy input for a low temperature Rankine cycle. Okay, using ammonia as the working fluid. The unit develop output of 18 kilowatt. So the output of this Rankine cycle, low temperature Rankine cycle, is actually 18 kilowatt, and energy conversion efficiency is 8%. Now it requires its energy input at annual mean temperature of 82 degrees Celsius. Use the Rebel and Insel analysis to calculate the pond area for values of depth L2 varying from 1 to 3 meter. So that the area is minimum for a particular value of L2. Plot the variation of area versus depth and the radiation and ambient temperature. The annual average daily global radiation is given, and the annual average ambient temperature is given. So basically this is Hg bar, right? Uh, and this is your Ta bar. Okay. Uh, Depth is your L2 is varying from 1 to 3 meter. Okay. Your phi is given and your conversion efficiency is given. Okay. So let's see. So this is say your solar pond. Okay. The hot water from the solar pond is actually fed into a basically used for a heat transfer in this Rankine cycle. Okay, where its output from the turbine will be your 18 kilowatt, and your efficiency of this cycle is 8%. So we know the output from this particular cycle, and you know the efficiency. We can calculate actually the input power required for this particular Rankine cycle. That will be the actual load requirement. So okay, so if we'll see, this is what I'm talking about. So for a Rankine cycle, first we'll see your efficiency is given, your output power is given 18 kilowatt. We can calculate the input power. This input power is actually your load requirement, your Q load, right? We can know what is the basically your heat rate, heat transfer rate required for useful energy. Okay. Okay, your now let us calculate the values of the effective angle theta 1 and theta 2. So this theta 1 and theta 2 used in this equation is for equinox day. Okay, equinox day at a date 14 o'clock. Okay, for that we need to calculate this particular theta 1 and theta 2 value. We already know the cos theta value for horizontal surface, right? We know the phi, we know that okay, so for equinox day, your your sun is directly shining on your equator, so your declination angle will be 0, right? So your delta will be 0. You know the omega is 12 o'clock. For 12 o'clock it will be minus 30, right? It will be minus 30. We know the phi, we know the omega, we know the delta. We can calculate your theta 1. We can, from theta 1 you can calculate your theta 2, right? Okay, so you can calculate your theta 2 using your Snell's law. Now your kj dash is basically kj upon cos theta, where j is from 1 to 4 depending on which wavelength we are talking about, if you remember the table. Okay, and cos theta 2 angle is your angle of refraction. Now let's see. So your theta 1 and theta 2 is basically, so your theta 1 was 40.49 and your theta 2 is 29.22. Okay, so your theta 1 and theta 2 values lies between, so theta 1 was 40, right? So your theta, this is the basically range in which your theta 1 and theta 2 lies between 30 and 45 uh, degree of incidence angle, or you can say 22 and 32 degree range of angle of refraction. So we can calculate tau, right, using interpolation for particular theta 1 and theta 2, depending on any value. For say for theta 1 or theta 2 we can calculate tau r. Now we can put all the values into the equation. So we know that temperature that, so in question it has been mentioned that your energy input at an annual mean temperature of 82 degrees Celsius is required. Okay, so you know the, okay, this value 82, you know the ambient annual ambient temperature, you know the tau r value. You have just calculated this Hg bar value is already given in the question. The thermal conductivity is, for water is this 0.648 watt per meter per Kelvin. Now for this term we need the tables for different wavelength A1, A2 and A4 value. You will see this value and corresponding to particular wavelength, the A1 and A and K value could be put into the equation, and we know K1 dash is your K by cos theta 2. So we can put all this value into the equation and we can finally get your area of pond value. And basically this was for 1 meter. Similarly we can calculate it for 1.5, 2 or 2.5 and 3 meter, and we can also calculate its annual collection efficiency. So this is how we basically calculate the area required for different depth, and we can see how it actually varies. Okay, now let's see some uh, questions. Okay, so this is the first question. What is the thermal energy storage system design depends on? Which of these factors? Okay, this is the first question. The thermal energy storage system design depend on which of this factor? Okay, we got one answer. So the thermal energy storage uh, system design depend on obviously what on the temperature difference we are going for, on the capacity of the system, and also on the cost of the storage system. So the correct option is option D. That is the right answer. Okay, now this is the next question. The storage capacity of a solar thermal. So we are now talking about solar thermal storage system. Now that will depend on which of this factor. Right. So we have got one answer, option D. So if we're talking about solar thermal storage system, then obviously it depend on whatever solar radiation is available at that particular location. It also depend on what is the physical and chemical properties of the storage medium that we are going to use, and also obviously depend on the thermal process nature. Okay, so the option correct option is all of the above. Now, this is the next question. What is the desirable properties of a phase change material? Okay, is my screen visible to you all? Okay. Now is it visible to you all? Whatever I'm saying, sharing. Okay, good. Alright, let's see this question also. So, we have been asked about what is the desirable property of a phase change material, PCM material. So, obviously, it should have a high latent heat of fusion, right? So, higher this value will be, more will be the energy released while it will change the your phase, right? There should be small volume change during melting, obviously. So, a more complex system could be designed. It should have minimum supercooling and superheating, and also it should have a high thermal conductivity. So these all are the basically desirable properties of a phase change material. So option B will be correct. Okay.
Excuse me, ma'am.
Yes.
Question slides are not showing.
It's again not showing. Okay, let me see.
No, no, something other.
Okay, maybe some internet lag issue, or maybe there. Let me.
Madam, it is shown to me. So I think there is an internet issue there, but it is visible for me.
Okay, is it okay? So there might be some internet lag or issue at your end. If okay, so now is it visible? You can just log in back, log out and log in back. Then it might be visible to you
Yes,
also.
yes, ma'am. It's come.
Sorry.
It's come. Clear,
Okay,
ma'am.
okay, okay, okay. Now it's fine, right?
Yes, ma'am.
Okay, okay, okay. Okay. The next question is this: what could be a thermochemical storage system application could be? Is it for low, medium, or high temperature application? Okay, we got one answer, which is option B. Okay, let's see this question. It's a um basic question. What should be the application range, or say, for a thermochemical energy storage system? So for it's basically medium and high temperature application from 100 to say 1000, even 1000 and 1200 degrees Celsius also. So its temperature varies from say medium to high temperature application. For low temperature application, you can go for your um, basically your solar pond is one of its example, right? So your flat plate collector is also, if you can say, it's basically sensible heating is only taking place. It's if you're going for water based flat plate collector, right? Okay, so the correct option is option second, and third it will be your option C. Now the percentage of energy absorbed in the surface convective zone of a solar pond is. Okay, so if you might have paid attention to the lecture slides where different amount has been mentioned, how much is incoming, how much is lost. We have also some solved one numerical also, where around 28.5% is lost to the surrounding, and around 30% has been, if you remember this curve, this is the depth, and how much energy basically has finally reached to the bottom. Okay, so this is the depth. Okay, so out of say 900 was the value, only 30%, about 30% was lost to the surrounding at the surface only, and the only 30% is basically, so say, let me draw it. So this is the different zone. Okay, so about 30% of the incoming energy is absorbed in this basically surface convection, your uppermost convection zone. Okay, this zone. Now this is another question. In a non-convective solar pond, the maximum temperature is obtainable at which position? Okay, so if you remember this, just I've explained the different zone into the solar pond. Okay. So in case of non-convective solar pond, where convection is not taking place, this we are talking about this zone, this middle zone. The maximum temperature will be obtained at the bottom surface, right? So uh, basically these are the question different theoretical question based on the solar pond. We just need to have an understanding of what different zones or how the temperature and concentration varies in different zone, where is the like particular depth at which how much most of how much amount of solar radiation is being absorbed in different zones. So these are just the theoretical question based on the solar pond. Okay, so just to check your understanding. Now the next question is, which of these following method are used to accomplish a non-convective mode of solar pond? Okay, see where this question is also not directly given in the your slides, but if you want to accomplish a non-convective mode of solar pond, this all this method are used to basically maintain your non-convective mode in a solar pond. Okay. Okay, this is the question, a numerical question. Uh, that we'll just solve now. Okay, so this i'll I'll give you a few minutes to solve this question, and then we can look at the solution for the same question. I'll just explain in detail. Okay, is my screen visible now? Okay, fine. It's visible, right? So let's solve this question. So what's given in the question is a well mixed water storage unit. So a well mixed water storage unit is there. So the mass of this water in the storage tank is given 3000 kg. Okay, and is provided with an auxiliary heater of 3 kilowatt shown in the figure below. That ambient temperature, so ambient temperature is given 18 degrees Celsius. The rate of mass withdrawal to the load, so this is given 200 kg per hour. This is given. Okay, assume that there is no heat gain to the water, no heat gain to the water. Okay, uh, and the auxiliary heater switches on when the temperature of the tank falls below. So when the temperature of the tank falls below 45 degrees Celsius, the makeup water enters at 24 degrees Celsius at the same rate, at the rate of withdrawal to the load, right? So at the same rate, 220 kg per hour. Now the overall heat transfer coefficient between the liquid in the tank and the ambient air. So what is given is, this is 6 kilowatt. So it's given. So area is also there, no? Right? So per meter square. So kilowatt per meter per degree Celsius. Okay. Now the surface area of the tank is given. So say the area of the tank is given 10 meter square. Consider the specific heat of water to be 4.2 kilojoule per kg Kelvin. We have been asked to calculate the present temperature of the tank. If the present temperature of the tank is 46 degrees Celsius at 5 o'clock. So at 5 o'clock, the temperature of the tank is given 46 degrees Celsius. What will temperature after 1 hour? So at 6, what will be the temperature of the tank? This is the first question. And the auxiliary heater is switched on at which time? So the time has been asked. So these are the two questions, right? Now let's see how to solve this question. Okay. Sorry, just a minute. Okay, let's see. So some of the assumption that we have already made is that Cp is constant, right? It will not change with temperature, and that is 4.2 kilojoule per kg per Kelvin or degree Celsius. And we are also neglecting the heat capacity of the tank, right? Those were the two assumptions that we started off, right? Neglecting heat capacity of tank. So whatever heat is been given, it's utilized by the water only. Now the mass was given of the tank 3000 kg, right? What else was given? Mass flow rate to the load was given 220. It was 220 kg per hour was there, right? Now ambient was given 18, and Cp of water is already we have written at 400 kilojoule per kg per degree Celsius. Now the first question was at 5 o'clock. The temperature in the tank was 46 degrees Celsius. Um, what is temperature at 6 o'clock after 1 hour, right? That was our question. So first we'll calculate the heat capacity, right? So the heat capacity of water, we know that equal it's basically mass mcp, right, of the liquid. So it will be 3000 into cp is your 4.2. So if we'll multiply it, it will be okay 12,600 kilojoule, okay, per kelvin. So it was in kelvin, right? Now if we want to calculate the heat to the load, rate of heat transfer to the load basically, so it will be into cp into your, right, this is the liquid temperature in the tank to the ambient temperature, right? So we are talking about this, right? So this was at T and the ambient is T, right? So if we'll calculate it, it will be 220, it is kg per, it was in hour, right? Into it will be 4.2 kilojoule per kg Kelvin, and TL is, so this is 46, right? And ambient was I think 18, it was 18, right? So this will be 8 and this will be 2, right? So if we'll solve this, you will get this is the actual heat required by the load, right? Now we also know this relation, right? QU minus Q load minus UA, this is TL minus TA upon QU minus Q load. This is the initial temperature minus TA. This is equal to e to power minus your UA T, your heat loss, and then this is heat capacity into your time. This time is in hours, right? This was the formula. We already know that in question your Q is full is given 0, right? This is given 0. We know the value of Q load, that is at 5 o'clock, right? We know Q load at a 5 o'clock. Now we know the time we have to calculate after 1 hours, right? So we know the initial liquid temperature, we need to find this temperature. We'll put all the values. So this will be 0, this will be 0, and your Q load is basically 25872 minus UA delta T value is, so UA delta T value was, just a minute, so it was basically 6 kilowatt, right, per meter square per degree Celsius. So this is 6 into area of the tank is, so note the unit, so it's only U, right? It's 6 kilowatt per meter square per degree Celsius. It's overall heat loss coefficient, okay? And your area of tank is given 10 meter square. So that's my mistake. So okay, I'm sorry. So this will be 6 into area of the tank is 10, right? Into TL is the unknown value, ambient is 18, and this will be 0 minus 25872 minus 6 into 10 into your initial temperature was 46 degrees Celsius at 5 o'clock minus 18 equal to e to power minus 6 into 10 upon heat capacity is 12 600, and we are calculating after 1 hour, right? So when we'll solve this, your TL will be at 6 o'clock will be if we solve this, it will come to be 44.3 degrees Celsius. Okay, now the next part was okay. The next part was to calculate the time at which the auxiliary heater needed to be switched on, right? So we already know the formula. The condition that if the temperature of the tank, water in the tank drops below 45 degrees Celsius, right? Then your this auxiliary heater needs to be switched on, right? That is our condition. So if I'll write this formula again. So we have been asked about what is the time for the basically to switch on this auxiliary heater when this that the condition is when this TL reaches to 45 degrees Celsius, right? So okay, okay, so let's see this. So your 46, what's happening? Okay, let me see. Okay, at 5 o'clock, it's not coming. Okay, at 5 o'clock, the temperature was 46, right? So we'll put all the values again. So it will be 0 minus 25872 minus 6 into 10 into this will be 45 minus 18 upon this is 0, this is 25872 minus 6 into 10. This is the initial temperature of the liquid in the tank was for 46 degrees Celsius, and this is will be 6 into 10 upon MCP was 225. Oh, okay, it was 12600, and this is the time that we need to calculate the time required uh, 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 for the liquid temperature in the tank to fall from 46 to 45 degrees Celsius, right? So when we'll solve this, the time will be uh, in 0.532 hours. Okay, let's see in what terms the question has been asked for in the question. Okay, so it's in hour only. Okay, so So the temperature after 1 hour was 44.3, and the auxiliary heater to be switched on was 0.532. So this is option C. Okay, so this is how a question is solved for well mixed water storage system. In your assignment, I think all of the questions are on theoretical only. So these are some numerical problems, and also the numerical problems are well explained in the lecture also. Those to pay close attention to those numericals. So the question might be framed on that also. So I will end the session now. Uh, I hope this session was useful to you, and again we'll meet in next session. And thank you all for listening.